So welcome to my garage. Here we have the shelves of much junk. We've got the table with the project on it that I haven't touched in 2 years. We've got the giant Alpha Phoenix logo on the wall. But today, I want to talk to you about the laser that I keep by the water heater. This laser is capable of turning on in just a couple nanoseconds, like ramping from off to full power in the span of maybe 5 nanoseconds. Today I want to take a video of the light leaving this laser, traveling across this room and hitting the garage door 18 feet away. So that distance is about 18 feet, about 5.5 meters, but I actually like using feet for this project, sort of out of character, because 1 foot is almost exactly 1 light nanosecond. This is how far light travels in a nanosecond, 1/1000th of a second. That means that if I'm fast enough, if I can take a picture of this wall every billionth of a second, I will be able to record 18 frames of video in between the light leaving this laser and the light hitting the garage door at the other end of the room. In order to record such a video, I'm going to use this camera that I built. Now, I have wanted one of these things for 12 years, ever since this group at the MIT Media Lab published an incredible video of light passing through a bottle of water at 1 trillion frames per second. If you haven't seen that whole video, you should go watch it, because it's amazing. I was fascinated, but somewhat put off by the $250,000 price tag. I realized about a year ago that the oscilloscope-based technique that I was using for a totally different project, trying to measure waves of electricity on wires, could be repurposed as a poor man's street camera like those researchers were using. Clearly, this sort of thing has been done before and done better, but my goal was to keep it cheap. I wanted to build the minimum camera capable of observing light move.
In a cave! With a bunch of scraps!
And the final bill of materials for this whole setup on the table here is less than $1,000. So in this video, I'm going to tell you how this camera works. I'm going to talk about how I built it, what sorts of problems you might encounter if you try to recreate this work. And of course, there are going to be some really cool videos of light shooting across the garage at the fastest speed that anything ever moves. Here's a picture of the laser illuminating the wall captured on my phone, and here is a video of the same scene captured by my custom lightspeed camera. So yeah, this is 1 billion frames per second. It starts totally dark because there's no light in the room. Then the laser turns on and you can see light rush towards the garage door, illuminating all the shovels and rakes and whatnot on the wall. Eventually, reflected light has enough time to bounce around and the whole scene fills up with light. Every frame of this footage lasts 1 nanosecond. That's 1 billionth of a second. And I'm playing the footage back for you now at just 5 frames per second. If you wanted to watch 1 second of real time at this frame rate, it would take more than 6 years. That's how fast light is. I couldn't resist the anti-clickbait of just putting one of the hero shots here at the start of the video, but I am going to make you wait until the end for the laser hitting a disco ball at 1 billion frames per second. Honestly, I haven't filmed it yet, but I think it's going to be really cool. So how does this camera actually work? Well, to start explaining that, I'm going to watch a car drive past through a very small hole in the wall. Bear with me. The first thing we're going to need is a hole in the wall. There we go. Nah, I'm just kidding. I don't have enough subscribers to go drilling holes in my house for every video. We'll just lift the garage. Okay, so now instead of drilling a hole through my garage door, I'm just going to put a hole through this piece of black poster board. Now, let me find it in here. It normally drops to the bottom. Shoot. Got it. Now, if I put this in my piece of black poster board, we have our hole in the wall. Now, if you look through this hole in the wall, you can see the outside world. Like, there's light that passes through this hole in the wall. And the important thing is that if you change your perspective, if you look through that hole in the wall from a different direction, you see a different part of the outside world. We can move again, we can see a different part, we can move again, we can see a different part. No matter where you are, you're getting a different part of the scene. If I'm standing here in the garage looking through that aperture, all of the light coming my way has to be coming from a very specific direction. I mean, obviously there's not going to be light that comes in and like makes a bend and then heads my way. Right now, looking through that hole, all I see is the gray of the asphalt road. But if I wait, just for a split second, I see white and then it turns back to asphalt gray. Maybe a car went by. If I were the scientific type, maybe I'd want to record some data. If I was plotting the color I see through this hole over time, it might look something like this, where it's dark road color, then suddenly it's bright, presumably a car, then it's dark again. That lets us establish that at this particular time, the car was at this location. But what does that really buy us? I mean, not very much by itself. Clearly, we need more data. If instead I was looking through the same hole in the wall, but I was standing over here, I could have still seen the car, but I'd only be able to see the car when it was in line with my new vantage point. If I make the same plot, starting at the same time, I would see the car later. It would look something like this. Likewise, if I was standing over here, I would have seen the car earlier. If we add a lot more observers at a lot more positions behind the hole in the wall, we could track the car the entire time it was moving, even discern its shape. This is exactly what a camera sensor does. It just only saves the average color it sees in each direction, not a mini picture like I'm showing in this animation. The instant this laser turns on, it sends a signal back to the oscilloscope over there through this cable that basically says, start recording. And at that point, the oscilloscope is recording everything it sees from the light sensor inside this camera. But the light sensor doesn't see any light because light hasn't had time to get from the laser to the detector. Eventually, light is emitted from this laser in many different directions, and let's say that some small fraction of that light hits this exact spot on the wall. When the light from the laser hits this spot on the wall, it reflects again in many different directions, but some of that reflected light is going to find its way over to this mirror, which is going to reflect it down into this lens, which is going to focus that reflected light into this aperture and into my light sensor that tells me how bright the light is at any given nanosecond. Just like with the example with the car driving by, this generates a graph like this, where we see the brightness of light observed by this sensor as a function of time. Here we can see it was dark, then it got really bright when the laser was on, then it got dark again once the laser was turned off. Now you may be saying, you've only got one sensor in there. How can you possibly record an entire video's worth of pixels? And I cheated. I'm not recording a single event with this camera. I'm recording thousands of identical events. And every time that that laser fires, I've got this mirror pointed in a slightly different location, looking at a different part of the wall. It's impossible to tell in real time, but this laser is actually blinking on and off about 10,000 times per second. That means that whenever I have the mirror pointed at a different part of the wall, I can take the most recent trace off the scope and it will have the data that I want. If we aim this mirror at a different part of the wall, we can work through the same exercise again. Light leaves the laser, hits maybe this spot on the wall, and then travels over to the mirror, bounces off the mirror, goes down, focused, aperture, light sensor, whatever. But because the speed of light is a thing, and this second route is longer than the first route, when the mirror is pointed at this part of the wall, we're going to detect that signal later. These two traces become pixels in our final image. You can see the first one gets bright, then the other one gets bright, and if we fast forward to the end, you can see the left pixel also detects the light turning off before the right pixel. Now, a lot of viewers may have noticed another sticky point here. When the camera is pointed at the second location, why can't light bouncing off the first location on the wall still get to the sensor early and mess up the result? And that's why I added the aperture in this funky optics train. Any light that doesn't come from the exact location I'm pointing at with the mirror will either bounce off the mirror and miss the camera entirely, or it will enter the lens at an angle and get focused onto a piece of black plastic instead of the light sensor down below. This is exactly what the aperture is for in a real camera lens, and it's functionally equivalent to viewing a scene through a hole in the wall. This setup does need work. Even if I hadn't snapped part of it while filming a piece to camera a few minutes ago, I need to replace this whole setup with like a brushless gimbal of some sort. These hobby servos are just not giving me the resolution that I want. If anybody knows an easy way to do that, I'd be all ears. But honestly, this whole pointing mechanism with the mirror and the lens and the whatnot was the easy part of this project. I threw this mechanism together in like a week of coming home every night from work and doing CAD and printing parts until I had this prototype. The difficult part was the light and the light sensor. Think about this frame. I wanted to get a video of light moving from one side of frame to the other, which takes a handful of nanoseconds. In order to properly light this scene, I need a light that turns on in significantly less time than that. Let me show you what I mean. This is an idealized room that's 1 pixel tall, and I'm simulating a light turning on at the left. If this light source takes 1 nanosecond to ramp from off to on, we would get a video that looks like this. The light turns on and appears to propagate across the screen. If that light takes a few frames to ramp from off to on, we would get something that looks like this. The partial brightness light would start propagating across the room before the light was at full brightness, which sort of smears the boundary, but we can still see a propagation. This is actually very close to what I was able to capture in real life. But if the light was significantly slower, say 50 nanoseconds, which is still absurdly fast for any reasonable light source, we don't see anything useful. Yeah, technically there's light propagating across the room, but the width of this front is wider than our field of view. So it would look like the whole room was just slowly fading into view, which doesn't make for a very compelling video about the propagation of light. So I am going to try to turn on the regular LED strip lights in the garage as a comparison. Yep, got it. All right, so my lights in the garage turn on in 6 milliseconds. Milli, that's awful. That is 6 orders of magnitude slower than what the laser does. Wild. Basically, I needed an insanely fast camera flash to take my pictures. Now this significantly limits our choices for both lights and sensors. You need a light that can go from off to full brightness in just a few nanoseconds, and you need a sensor that can go from detecting no light to detecting all of the light in just a few nanoseconds. Only if you have both of these things will you be able to observe propagating light and not just a room slowly getting brighter. My first choice for a light that could turn on very quickly was actually an electric spark. I'm not sure how I would have repeatedly triggered thousands of sparks to create uniform illumination for the scene, but I did expend some effort trying to time the light emission from a spark and deemed it way too slow.
Something notable in 1.2 microseconds, but I want like 1,000 times less than that. It's gotta be like there.
Knowing what I know now, my sensor was actually way too slow when I was doing these experiments, so I wasn't giving the arc a fair shot. It's certainly better than I measured, but I'm sure it also pales in comparison to the laser driver I ended up using. For the electricity wave experiments, I'd been playing with these extremely fast rise time Schmidt trigger chips, and I was doing things like ganging a bunch of these circuits in parallel and pumping that "turn on right now" signal into random LEDs that I found in my old box of mystery LEDs. Needless to say, this didn't work very well. A little research turned up that LEDs and lasers should both be able to turn on pretty fast, in the realm of tens of nanoseconds if you cram enough current through them. But there's no way the circuits I was building could move electrons fast enough to overcome the capacitance of the device in a reasonable time frame. And by reasonable time frame, I mean a nanosecond, which is kind of hilarious. Through all of this, I was becoming increasingly frustrated that LiDAR worked. I mean, detecting nanosecond pulses of light in broad daylight is a commercial thing. Like, it's done. That's how a lot of self-driving cars do it. And for some reason, I couldn't recreate this for any reasonable sum of money. Most of the LiDAR drivers I could buy online were absurd, but somebody recommended this miniature driver circuit that was pre-made. It claimed to be able to push 10 amps into a laser diode and turn on in a few nanoseconds. It was still a really huge fraction of my target budget, but exasperated by the math telling me that this was a really, really hard problem to solve, I went for it. I also got some cheap red laser diodes under the assumption that any old diode could get really bright for 100 nanoseconds if you crammed enough current through it. With this driver, you get a readout pin, and I could see that yes, indeed, I was shoving current through my laser diode really, really fast. But my sensor wasn't detecting it really fast. If your sensor is slow, you might have a situation where your light turns on really fast, but the recorded light intensity lags behind. There's this great bit in a Corridor Crew video where they talk about motion blur never stretching out longer than a frame.
You can turn on motion blur. If you don't set it up completely correctly, the size of the motion blur can be too long for how far the thing should be moving. So like, let's say in one frame an object is here, in the next frame it's here. If there was to be motion blur, that motion blur streak could not be any bigger than the streak from this point to this point.
But if your light sensor's output can't ramp as fast as you're recording data from it, that's actually exactly what happens. It's multi-frame motion blur that happens over a couple nanoseconds. If this same type of temporal distortion was in a regular video of regular things, like me talking right now, this is what that might look like. All of the motion is sort of smeared out over time. Even the best videos I've captured with this camera so far have probably 5 to 10 frames of meaningful motion blur. And that's because it takes 5 to 10 nanoseconds to record a single photon using this light sensor. This is what the signal from a single photon actually looks like in this setup. The signal rises from off to on in 3 to 4 nanoseconds, which is okay, but then the next bunch of frames still get signal from that same photon. In the jargon of video recording, I guess this would be like a somewhat blurry 3600 degree shutter angle. It's just a very bizarre limitation of the specific sensor I chose to work with. Unfortunately for me, I did not in fact have a lot of photons coming in. Let's do some back of the napkin math. If we have a light source being driven at 10 amps, which is enormous, in a best case scenario, we get 1 photon out of the laser for each electron we pump in. So 10 amps divided by the electron charge says we're creating 6 times 10 to the 19 photons per second. If those photons are leaving the laser and spreading out over a wall that's 20 feet long and 10 feet tall, then we have about 300 trillion photons hitting each square centimeter of the wall each second. If we assume we've got our mirror and lens set to record a spot on the wall that's pretty small, maybe 4 square inches, and those photons are spreading out through the room again before they reach the camera, then we're looking at a few hundred billion photons entering the camera every second from our laser. Now that sounds like an awful lot, but remember we're trying to record video at 1 billion frames per second. And even at what would classically be considered a 360 degree shutter angle, that means we only get to collect light for 1 billionth of a second, leaving us with just a few hundred photons per pixel per frame, best case. In reality, I was expecting to be dealing with just tens of photons per pixel per frame. And when a light is so dim that measuring the brightness of that light is basically just counting photons, you're going to need an absurd level of amplification. The first tool that I used to convert this optical signal to an electronic signal was a woefully insufficient silicon photodiode. Silicon photodiodes allow a single electron to pass through the device into a wire for every photon that enters the window. If you look at my oscilloscope specs to see the minimum detectable signal that this oscilloscope could ever possibly hope to measure, we would need to push something like 100,000 electrons into or out of this probe wire that's plugged into the scope. Clearly, if the light sensor is only able to get tens or maybe hundreds of electrons, that's not going to happen. The light's going to turn on, the light sensor is going to start chugging electrons through, and this wire is going to slowly fill up with electrons until that scope can measure it. Personally, I saw a 1 nanosecond rise time on the datasheet and got excited. So excited that I forgot to do that math I just showed you, so until I tried it, I didn't realize this sensor was going to get me nowhere fast. I think commercial LiDAR systems mostly use avalanche photodiodes, but I skipped all the way to the most sensitive light sensor I could get my hands on, a photomultiplier tube.
Wow. Never really looked at one of these.
Photomultiplier tubes, or PMTs, are vacuum tubes. I love the elegance of tubes, and a ridiculous amount of modern physics was first figured out by just shooting electrons around in vacuum tubes and looking at stuff glow really carefully. But PMTs specifically are amplifying sensors. A PMT can take in a single photon of light and release millions of electrons into a wire, a real electronic signal that can be recorded by other equipment. If all of my hobby experiments have taught me anything about radio frequencies, it's that attaching a 47 ohm terminating resistor with blue tape is a great idea. I set up the simplest test I could, a laser shining straight into the detector across the table. And you turn off all the lights again. Yes! Look at that! That is so fast. That's so fast. Can I block it? Oh my God. This is gonna work. This is the first time that I've been convinced that this is gonna work. Because I was emitting light from one device and detecting that light with another device, and the rising signal on the detection went from low to high in less than 10 nanoseconds. That was a lot of work to get there, but that's all I needed. At that point, I knew it was going to work. The realization that I finally had a fast enough detector circuit set off a week of playing with lenses, fiddling with servos, doing CAD well into the morning, and giving my seldom used printer one heck of a sudden workout. By the next weekend, I was ready for testing. After assembling the pivot setup and making sure I could run the motors, I disabled the motors and tried to detect light bouncing off a white reflective board sitting directly in front of the camera. I'm not seeing anything. If there's anything blinking out there, this should see it. Output control voltage 0 to 5. Okay, how did I make it work the other night? This was just about the easiest test task that you could imagine. Plan A does always go up in flames. At this point, I could tell that I was getting photons from the laser, but there was just so much light in the room that my signal was being drowned out. So I went on a kick to darken the room. Every window with a street lamp behind it, every battery charger, every random LED that makes a bit of light in the garage, covered up. All of the electronics I needed to run this system went into a big black box with a curtain behind it. And this reverse dark room cubby became my mission control. For actual measurements, I would remote control my laptop from upstairs, so I never even had to open the door and let light in from the kitchen. And let me tell you, if you walked around that room, it was dark. By the virtue of much averaging and noise subtraction, I was able to get this. Clearly there was light moving from one side of frame to the other, but the resolution was awful. I couldn't actually tell what I was looking at. I needed more light so that I could spend less time gathering each pixel. One real application for technology like this is LiDAR, and because people don't want their self-driving car going down the street to look like a rave on wheels with blinking lights all over it, most LiDAR lasers are infrared, which makes high-power visible lasers, especially ones designed for pulsed operation, very difficult to come by. I also wanted a visible light because I wanted to be able to see it with my own two eyeballs and set up an interesting shot on the wall. Also, the PMT has a sensitivity that totally falls off by 3 orders of magnitude between 8 and 900 nanometers. So I can't see infrared, you can't see infrared, this camera can't see infrared. I needed to find a high-power visible laser. Okay, this is really cool. It's so bright that I can actually guide the beam now. So I know some of it's going to hit this wall, and then some of it's going to keep going, and it's going to hit this area. So I'm going to get this table out of the way that I will undoubtedly walk into in the dark later. Signal! Look at this. I was fighting for scraps, and now I have to turn it down. So I was maxed out. I was here. The signal's 3 miles below me. This is gonna work, and it's gonna work fast. This is gonna work as fast as I can move the motor. Why is OneNote using 22% of my CPU? Yes. Yup. Oh my God, that's the circle on the wall. This is the ceiling. I've been looking at the ceiling. That's really cool. And then it goes away, and then the ceiling goes away, and then the sink keeps glowing for a long time. Unfortunately, after this, when I tried to record the hero shot for this video of the light traveling the long way across the wall, I had a mishap. The laser went dark. That is nowhere near as bright as it should be. Now the failure mode here is pretty interesting. The outer edges of the beam are still kind of visible, but the center is gone. I've got a whole video about how stimulated emission from lasers works, but I don't talk that much about the mirrors. In a diode like this, the facets that reflect the light back and forth inside actually absorb a tiny bit of the emitted light and warm up. If those facets get too hot, they can melt or burn or otherwise stop being a window, and then they absorb much more light, which causes them to get even hotter, which causes them to degrade faster. You get the picture. Your laser diode's going to have a bad time. The laser got hot enough to melt the solder attached to its leads, and it almost fell off the driver. So I had to wait a couple weeks to get new diodes and get everything set up again. But then I got to work figuring out how to tastefully illuminate my entire garage with a single laser diode, running at the rated current this time. And I got some really cool shots. And now the moment we've all been waiting for. It's like covered with glass dust. That's a ball covered with mirrors, all right. That's not a 1/4 inch. What kind of thread is it? Nope, it's gotta be some funky metric something. Oh, I don't see the laser. I guess the glasses really work. Here somewhere, yep, there it is. Oh, you do get a bunch of them. And then all the stars show up. That's really cool. That's really cool. Yeah, the stars show up fast because they're coming this way. The last one goes out. That's really neat. I need to get like a lot of mirrors. If you're still watching this video right now, there is almost certainly an image of something in your head that you think would look really cool filmed at 1 billion frames per second. So let me know what that thing is in the comments down below. Towards the top of my personal list is to look at reflection and refraction. It's going to be difficult to get like a giant basin of water with a clear wall that fills up most of this area, but I would love to be able to recreate a demo like this one from today's sponsor, Brilliant.org. It would take hours of work in real life on this wall to set up different conditions of angled rays of light. But if you really want to get an intuition for how refraction works, at least I would need to see a lot of different conditions and sort of get a feel for it. It turns out that when I was playing through this particular unit, I didn't actually spend enough time with the demo before answering wrong. Twice. But this actually turned out to be a great thing, because if you get an incorrect answer, Brilliant's courses explain to you exactly what went wrong. And then this unit even tied the correct answer back to real technology in the form of fiber optic cables. Honestly, this one question on this one puzzle, changed how I think about total internal reflection as a concept. It's fantastic. Brilliant has courses on loads of topics extremely relevant to the sorts of projects that I build and show off on this channel. Physics, math, computer science, lots of programming and AI courses. It's really great. And honestly, the puzzles and lessons are fun to play through. If you made it this far through this video, you clearly like learning stuff. You should go check out Brilliant.org. I've left a link in the description. So thank you to Brilliant for sponsoring this video. Thanks to you for watching this video, and I'll see you next time. Remember to comment with things that would look better at 1 billion frames per second.